Yeah, we are live.
Good morning, everyone, and thank you for joining. We are really excited to welcome you all in the Bootcamp 2024 Exploring the Cosmos. With this inaugural public talk, Mysterious Universe, presented by the esteemed Professor Patrick Dasgupta, we are delighted to welcome you all in this engaging experience, which will be having from today, June 21st, to July 21st, with the found memories of Dr. N. Ratnashri, because her dream was this, and this boot camp was his like a dream project every year, which he was doing it in planetarium. So just wanted to take that legacy forward with all the young minds and the respected professor and eminent team who had given their open-hearted support to us to make this long program come into shape. I really hope and encourage all students to come forward and take maximum advantage of this duration, ask lot more questions, get your doubt clarified. And this program is meant for all the students and young minds who wanted to explore the cosmos with all the details and nitty-gritty facts you wanted to get clarified with the experience package. So, not taking much time because we know that you have all came with a long ways and reported to planetarium on time today. So I quickly welcome Megha so that she can introduce Professor Patrick Das Gupta, and then we can start the program. I'm very much thankful to Megha, Rishabh, and Patrick sir for so much time differences. I think we all managed, and this was that zeal and enthusiasm in all of us to do something related to this what we call the outreach thing, which late Dr. N. Ratnashri was doing it. So I'm very thankful to everyone, and most of important to all the students who actively supported and participated in this program. So Megha, over to you. Let's start the program.
Thank you, Prerna ma'am. Good morning, everyone. First of all, again, a warm welcome to everyone on behalf of Planetarium in this boot camp. And of course, it's a legacy that we are following of Dr. Ratnashri. And welcome, sir. Everyone is fond of Professor Patrick Das Gupta, our very own sir, who have been teaching her for so many years. And welcome, sir. It's lovely to have you here today. And we know that we are at a huge time difference, and it's almost 9 p.m. You are in the different part of the world. And nonetheless, without taking any more time, I just want to introduce Sir one more time on this platform. So, after receiving the National Science Talent Search Scholarship in 1976, Sir joined BITS Pilani to do a 5 years integrated MS physics program. And in 1981, he took admission in the PhD program in Indian Institute of Science, Bangalore, but left for TIF or Mumbai in 1982 as a research scholar in the theoretical astrophysics group. And there he did his PhD with Professor Jayant Narlikar. Soon after submitting his PhD in 1988, he joined IUCA Pune as a postdoctoral fellow. And during 1989 and 1990, he visited University of Wales, Cardiff in the UK, and Paris Observatory as a senior research fellow. And until very recently, that is March 2024, Sir was associated with Department of Physics and Astrophysics, University of Delhi, where he joined as a lecturer in 1993, became a reader in 1996, and a full professor in 2004. So, sir, very warm welcome, and we are very fortunate to have you here today. Over to you.
Thank you. Thank you, Megha. So, first of all, I begin thanking Prerna Madam for organizing the boot camp, and in spite of many personal handicaps, she was able to present the whole program today. And I also thank uh, Megha and Rishabh for conducting this talk. And it's wonderful to interact with all of you. And anytime you want to ask questions, please feel free to ask questions, because science progresses by uh, making and asking difficult questions. Right. So I begin my talk by paying my tribute to the former director, late Dr. Nandiwala Ratnashri, who made pioneering contribution to stellar evolution theory during her PhD at TIFR, and then later on made wonderful research work on pulsars during her postdoctoral period. And after taking the directorship position in Nehru Planetarium, contributions to Indian astronomy history, particularly the Jantar Mantar, all the four Jantar Mantar of the country. Right. So now let's begin with the topic of my lecture. Since time immemorial, uh, the ancestors knew about sun and several planets. In the slide, you can see several planets. And of course, now the Pluto has been Plutoed in the sense that it's no longer considered as a planet, but a dwarf uh, solar object. And one of the mysterious aspect of planet Jupiter is something very often cited, and that is the red eye of the Jupiter. Here is the close-up of the red spot of the Jupiter, and you can see the red spot on the Jupiter is essentially formed by the turbulent circulation of the gaseous atmosphere of the Jupiter, and the circulation, because of the vortex and angular momentum, it has been persisting for more than 10 to the power 8 years. The clear understanding of red spot, although there are many theories, but there are still a lot of research activities going on to explain this Jupiter's red spot. So this is one of the mysteries of the solar system object, namely the red spot of the Jupiter. Uh, then we have Sun, of course, as the closest star around which our Earth goes around and completes a full revolution in 365.25 days. But Sun is only one of the few stars in the universe. Here in the slide, you can see a
Sir,
whole
I'm
lot.
sorry to interrupt. Are you changing the
Yes.
slides because the slides are not moving?
Oh, is that so?
Yeah.
Okay, let me.
Can you try
That's
in full screen more?
that's
Yeah, now
alarming.
it changed. So
Great, great. Yeah.
yes, now I can
Uh,
see Dr. Ratnishri's slide. It was
yes, but what I will do is I will go into the slideshow mode and check whether the slides are moving forward. All right.
sure, sure. Just if you can just check it.
Has it moved to the slide
It's
where
still showing the first slide. Can you move to the
oh,
second one?
the planets are they
No,
visible?
no, I can just see the the title slide, the first one.
Oh, I see. There's something problematic. Wait a minute.
Yeah.
Uh,
I think if you
if
click
I
on the
do
slide,
this, are you
yes,
able to go to
yes,
the second
yes,
slide?
now it's fine. Yeah, yeah, I think
The
we should do it
planets,
like that. Yes. Now I see the
but is
planets.
it in the full screen mode or not?
This is not full screen mode, but
Yeah, so that's the problem. If I
no
go
worries,
to the
sir.
full
It is
screen
visible now.
mode,
I think you can change the slide with the cursor on the side. That
let me
should work.
check whether. Um, hmm. Okay, so probably we'll have to get along in this manner without the full screen mode.
Right.
Is that
That's
all
fine.
right?
That's fine. Yeah,
Okay.
that's fine.
Yeah. So in this slide, of course, we show all the planets along with the sun. And as I mentioned, that one of the mysteries, although there are a lot of physical models that explain the red spot of the Jupiter, but the activities, research activities are still on to see what kind of turbulence, role of the turbulence and the vortex on the gaseous atmosphere of Jupiter causes this red eye to be persisting for more than 100 million years. Right. As I said, Sun is only one of the uh, many stars, to be precise, one of the 10 to 11 stars in our galaxy. And in this slide, you can see bright stars formed out of the gaseous clouds. And now there is fairly a good understanding as to how stars form from gaseous clouds. In the next slide, you see the latest telescope, the space telescope James Webb, which has taken the picture of this Carina Nebula, and you can see the molecular gaseous clouds from which stars are born. So, how are stars born? What happens is one of the gaseous clouds, due to a gravitational instability called the Jeans instability, the cloud starts collapsing under its own weight because gravity is always attractive and the cloud starts collapsing. But when a cloud collapses, it gets compressed. That means the pressure keeps on increasing and hence the temperature also rises inside. Just like when you compress a cylinder filled with gas, if you compress it, you will find that the gas temperature goes up, and when the temperature goes to very high level, then the nuclear region, it undergoes thermonuclear fusion, where effectively four hydrogen nuclei fuse to become one helium nucleus. And because the sum of the rest masses of the helium nuclei is more than the rest mass of the helium nucleus, the deficit essentially goes into photons or radiative energy purely from E equal to mc square formula. And therefore, a star shines because of the thermonuclear fusion that uh, in the main sequence stars, in which four hydrogen nuclei fuse to become one helium uh, nucleus, and thereby releasing a lot of energy, because some of the masses of four hydrogen nucleus is bigger than the rest mass of the helium nucleus. And then the atmosphere, the cooler atmosphere of the star, if it has an angular momentum, it forms a disk, and eventually the disk, the grains in the disk condense and form planetary system around the star. So star formation and formation of planets is fairly understood. And a star, for a great time, remains in quasi equilibrium because the gravity, which is trying to make the star collapse to a point, that gravity is counteracted by the pressure, because the star is very hot, and hotter the substances, greater is the pressure, because of the law that pressure is nkt, where n is the number density of gaseous particles, k is the Boltzmann constant, and T is the temperature. So the ideal gas law, which says pressure is equal to number density into Boltzmann constant temperature. So temperature being high, the pressure is very high. The pressure prohibits the star to collapse under its own weight. Right. You might ask, how do we know the stars that we see, what the temperatures are? It so happens most of the stars, the surface of the star emits like a black body. How do we know that? If you analyze the radiation and consider the spectrum, you can take the spectrum using a prism or a diffraction grating, and if you plot the intensity of radiation versus wavelength, you will find a curve which resembles the black body Planck spectrum. And by fitting a Planck spectrum, you find that the temperature, what the temperature of the star is. For example, for sun, when you fit the continuum radiation, which is close to a black body spectrum, the temperature comes close to 5,900 degree Kelvin. All right. Remember, to understand the objects of the cosmos, what we do is we use the laws of physics that were discovered in the laboratories on Earth, and we apply our understanding of laws of physics that we have discovered on the terrestrial laboratories. And when we apply it to understand the heavenly bodies, which are so far away that we can't even touch them, we find that the laws of physics do a great job in explaining the cosmic objects. So that's the reason why we have confidence enough that the laws of physics that we have discovered on the surface of the Earth are universally true, and we can use them to understand cosmic bodies. Now, where are the stars that we see located? The stars that we see with our naked eyes, they are uh, sort of organized in a disc-shaped galaxy. And here is an artist's conception of our Milky Way galaxy, in which the solar system lies on the disk. So this is the front view, artist's conception of the front view of our Milky Way galaxy. And you can see the spiral arms, and our solar system from the center of our galaxy is about 8 kiloparsec away from the center of our galaxy. What is a parsec? One parsec is 3 times 10 to the power 18 centimeters. That means 3 followed by 18 zeros, that many centimeter makes 1 parsec. 1 kiloparsec is 1000 parsec, and 1 megaparsec is 1 million parsec. 1 gigaparsec is 1 billion parsec. That means 1 followed by 90 parsecs. Because our universe is so huge, all the things, whether we are talking about mass, length, or time duration, they are astronomically large. And we have to, in astronomy and cosmology, we have to get used to this large numbers, because obviously mass of the sun itself, as you know, mass of the sun is 2 times 10 to the power 33 grams. That means 33 zeros that follow 2, that many grams. So obviously cosmic objects, they have to be described in terms of large numbers. Of course, our Milky Way galaxy is a spiral galaxy, but there are many kinds of galaxies. There are elliptical galaxies, there are barred spiral galaxies, there are irregular galaxies, and so on. How the galaxies have formed? Galaxies are essentially formed out of stars, gaseous objects, as well as a mysterious object called dark matter, which we know exists, but we still don't know what dark matter is composed of. All right. And here is a snapshot of the cosmos, and you can see that the bright objects are actually galaxies. Our Milky Way galaxy has 10 to the power 11 stars, but there are elliptical galaxies which you can see, which look somewhat reddish brown on the screen. Those are elliptical galaxies. Elliptical galaxies are much bigger. They can have stars of the order of 10 to the power 12 to 10 to the power 13 stars. Spiral galaxies, on the other hand, tend to be smaller, and it is the consensus is that elliptical galaxies are formed by the merging of 2 or more spiral galaxies, and that's the reason why elliptical galaxies are much bigger. I'll come to galaxies a little later. Okay. Now, how do we study all these cosmic objects? It is because of the powerful telescopes. Of course, Galileo was the first one to use telescope to look at the moon, the Jupiter, as well as sun. But now we have much more powerful telescopes, like, as you know, the Hubble telescope, the space telescope itself, is a large telescope having the optical system has a diameter of the order of 5 meters and so on. And now there is a project of having a 30-meter telescope on Earth, the so-called TMT project. And it is these avant-garde telescopes that help us in understanding the cosmos. You might ask, how do we know the distance of various cosmic objects? So one of the things that is used is the method of parallax. So for example, if you have a nearby object, so don't ignore that this is Alpha Centauri. Uh, Imagine that you're trying to measure the distance of moon from Earth. What you do is you uh, have one friend of yours, let's say, who is close to Arctic, and another friend who is close to Antarctic, and you tell them to look at the moon at the same time. That means they have to point telescope at the same time. Obviously, the telescopes will make different angle with respect to the local vertical, and from that you can figure out this angle, because the sum of the angles of a triangle is always 180 degree, as can be proved using Euclidean geometry. And because the base angles are known, this angle can be found out. And if this angle is known, and this distance is already known, because you know the distance between one point in Arctic and another point in Antarctic, you can always figure out using the latitude, longitude. What you don't know is the distance of the moon, and this angle is known and this distance is known, and using trigonometry you can find out any of these distances. And that's how you find out distances close to Earth. But if you want to find out the further away objects, you have to use a different baseline. Here, the baseline was one point on Arctic, the other point on Antarctic. For further away objects, you can use Earth going around Sun. So you observe a star in the month of July, observe another star, same star in the month of December, and the baseline is the diameter of the ellipse around which Earth is going around Sun. So this is the parallax way of measuring distances, and distances are very important. Without knowing the distances, most of the properties of cosmic objects cannot be ascertained. And it is through knowing the distances of planets accurately that Kepler established the three laws of planetary motion. In fact, Kepler's laws were the first laws in physical sciences that were uh, made in terms of mathematical objects. For example, ellipses, and the fact that square of the period of a planet is proportional to the cube of the semi-major axis. As you can see, Kepler was using mathematics to ascertain the laws of planetary motion, and is the first time that the physical sciences encountered mathematical laws. And it turned out that indeed mathematics is the underlying language to understand not only the fundamental laws of physics, but also different patterns that is present in cosmic bodies and universe as a whole. Let me skip this slide. Let me skip this slide. Now, before we go to galaxies, etc., let's look at some of the mysterious aspects of the sun. As you know, that there are these solar prominences and solar flares that time to time erupt from the surface of the sun. How do they, what is the physics behind it? As you know, that there is a Aditya L1 mission recently launched by ISRO. Aditya L1 mission is going to give us a lot of information about this solar prominences, what keeps the solar corona at such high temperature, 1 million degrees Kelvin, while the surface of the sun is only about 6,000 degree Kelvin. Now, solar prominences, you will find that they are anchored on dark spots. These dark spots were first discovered by Galileo, and these dark spots are dark because these are essentially, let me see whether I have here is a picture of a dark spot magnified. As you can see, the size of a dark spot, typical dark spot, is bigger than the size of the Earth. And these dark spots, you can see, they are dark because they anchor magnetic fields. These magnetic fields, because of the Lorentz force, they prohibit hot matter from the interior region to come into this region. And because there is lack of hot matter coming in, they are cooler, and that's the reason, in contrast, they appear dark. So in other words, the uh, dark spots and the solar prominences, they are due to the activities of the magnetic field and the convection current just below the surface of the sun. And a great deal of theoretical modeling is still going on to understand the dynamics of solar prominences, dark spots. There is a mysterious 11-year cycle of dark spots, which is, although there are a lot of theoretical models to explain it, but it's not clear which is the right model to explain this 11-year cycle of appearances of these dark spots, namely the magnetic loops coming from within and due to its own buoyancy coming out of the surface of the sun. So this is another mystery which needs to be resolved properly. Yeah, so this slide, as I said, that to measure distances of nearby star, you can use the baseline, which is the diameter of the, that means the total major axis of the Earth's motion around sun. Sorry that this slide came later. Uh, One of the fundamental laws of physics that is used in understanding heavenly bodies is the gravitational law, which says that if you have two masses, me, and the distance between them is r, then the force of attraction, the magnitude of the force of attraction, is Newtonian gravitational constant times me times divided by square of the distance. And gravity for normal matter is always attractive. And although gravity doesn't is not that important when you're talking about a table or a chair or a bottle, their shapes are largely determined by other forces other than gravity. But the moment you go to cosmic bodies, the masses are so big, and the forces, as you can see, are going as m square. Because of gravitational attraction is so large, most heavenly body, they get squashed under their own weight, and they are spheroidal in shape. Gravity overpowers all other forces because the masses of heavenly bodies are much larger. Let me continue. Yes, now from stars, let's go over to the galaxy. As I said, that Milky Way galaxy, the artist's conception, when you look at it face on, it looks having this, the spiral arms. At the center, today we know there is a supermassive black hole which weighs about 4 million times than the sun's mass. Okay, but if you were able to see the Milky Way galaxy from its side view, from the side view, it looks like a disk with the central region forming a bulge and the spiral arms in the disk plane. And there is a whole big dark matter halo about all galaxies. And as I told you, the dark matter is something that has attractive gravity, no doubt, but what we don't know is what is this dark matter made up of? Are they made up of very uh, unknown cold dark matter particles like WIMPs, or are they made out of ultralight cold dark matter particles? So a lot of research is going on as to what this dark matter is made of. So this is another mystery of the universe, namely, what is the nature of the dark matter? While for the solar prominences and all, the laws of physics that is important is the Maxwell's equation that tells you how electric magnetic field um, the dynamics of electric and magnetic field and how they act on charged particles. So, in other words, uh, what I want to emphasize is to understand the universe and its mysteries, we have to be very, very conversant with laws of physics and the tools of mathematics, which is the language of physics. Right. So let me skip all these slides and go to the evolution of the stars. So stars come in different kind of masses. The average star like sun, after billion years, it becomes a red giant when the core becomes helium dominated and envelope, which is still hydrogen rich, they start burning. And because the envelope around the core, the gravity is lower, so when it burns, the whole thing expands and it becomes a red giant. But the core, eventually, when the core is carbon oxygen rich, it dies as a white dwarf. On the other hand, if you start with a very massive star, how massive? Let's say 10 times sun's mass, then it expands to a red supergiant, and the core, when the core uh, has a mass more than the Chandrasekhar mass, which is about 1.4 solar mass, uh, it implodes, it just collapses, and the gravitational binding energy is released in the form of neutrinos, which dump their energy on the envelope, and the envelope explodes like a supernova. So the core, depending on the mass, can collapse into a neutron star or a black hole. So one of the mysteries is exactly how the supernova explosion takes place. For a long time, people could not, in numerical simulation, could not reproduce the supernova explosion. Now it is felt that the uh, you have to depart from spherical symmetry. You have to bring in asymmetry to reproduce supernova explosion. But this is one active area of research, and uh, uh, the last word has not yet been written on this. And you can see the crab. This is the crab supernova remnant, and uh, the supernova went off in the year 1054 AD. How do we know it? Because Chinese astronomers recorded that in this direction there was a new star that appeared, and uh, the astronomers have calculated from the size of the crab supernova remnant in that, and there is a pulsar uh, in the middle of this supernova remnant, and from this, the age that has been determined coincides with 1054 AD being the time when this exploded. Similarly, there's the Kepler supernova remnant that went off in the year 1604. Uh, and the last supernova explosion that was studied in detail is one that happened in the Large Magellanic Cloud. This is the supernova that went off in 1987A, and this supernova remnant is called SN 1987A. And the observation of neutrinos from this supernova remnant told us that when the supernova explosion goes off, 99% of the energy, the gravitational energy which the core collapses, 99% of the energy goes into the neutrinos. Only 1% goes into the mechanical energy that drives the blast wave of the supernova explosion. Let me skip, except I should tell you that that there are cosmic rays which are seen, and cosmic rays, the energy are as high as 10 to the power uh, 15 electron volt. The highest cosmic ray energy goes to 10 to the power 21 electron volt. And for a long time, people wondered, how do you have such high energy cosmic rays? What are the accelerators for these high energy particles? Today, it is understood that it is the shocked shells resulting out of the supernova, that particles diffusing across the shocked shells of the supernova, they get the diffusion to and fro across the shocked shells. That is what accelerates these particles. It's essentially is the bulk energy of a moving shock resulting from the supernova that drives the acceleration of this electrons, protons, and other nuclei. But the spectrum of high energy cosmic rays is still a matter of mystery. And um, how is it that you can still see 10 to the 21 electron volt cosmic rays in our coming to our Earth's surface is still a big mystery. So I'm going to highlight some of the problems concerning astronomy, cosmology, and which are still very active areas. Let me skip this slide. Yeah, here is the slide of how shockwave to and fro diffusion of particles that accelerate the particle. Don't worry. I mean, even if you don't understand, because I'm just skipping over very fast, if you raise the question later on, I will try to elaborate more. Then comes the neutron stars. As I said, that the core, if the mass of the core is less than twice the sun's mass, it'll collapse into neutron star. And how do we know that neutron stars exist? It so happens that neutron stars, they are also endowed with very high magnetic field of the order of 10 to the 9 to 10 to the even 14 to 15 Gauss. And the magnetic axis usually is not aligned with the rotation axis, just like Earth's magnetic axis is not aligned with Earth's rotation axis. And therefore, if you are far away from a neutron star that is rotating, the magnetic axis will be precessing around the rotation axis. And since the magnetic field is changing with time, changing magnetic field produces electric field, according to one of the Maxwell's equation. And therefore, it is these magnetic electric fields that accelerate. They essentially rip off the surface of the neutron star, that particles are accelerated, and in turn they produce electron and positron pairs, which are responsible for going along the magnetic field and producing curvature radiation. And the curvature radiation that you see pulse, because they are essentially being radiated along this cone. The cone itself is precessing about the rotation axis. And that's how pulsars were discovered, and pulsars confirm that neutron stars are formed. But many of the mysterious problems are associated with the uh, pulsation, the pulsing mode of the pulsars themselves. A clear understanding is not there. How do you have such coherent radiation? Are the electrons bunched to produce this coherent radiation? Similarly, there are neutron stars with magnetic field as high as 10 to the 15 Gauss. They are the magnetars, and magnetars pose a great deal of mystery, and a lot of fundamental problems like fast radio bursts are likely to be associated with this magnetars and pulsars, etc. So these objects, they hold many things for future interest, and a lot of active research is taking place in this area. So this is the Chandra X-ray telescope of the Crab pulsar, and the bright region are where the X-ray emission is highest, and you can see that direct X-ray emission itself is showing the evidence of rotation. Here is the Vela pulsar image. The X-ray photons have been, of course, converted into optical light, and you can see the presence of rotation about this axis. Now we come to galaxies. So this is a spiral galaxy which is almost appearing face on, and you can see the central region. By now, we know that all galaxies, big galaxies like spiral galaxies and elliptical galaxies, they house a supermassive black hole at the center. All right. So here is an elliptical galaxy. This is the famous 1980, sorry, M87 elliptical galaxy, and you can see the jet. And those who are interested in black holes, they must be aware of some time back this M87 uh, elliptical galaxy, the supermassive black holes, the the photon sphere around the black hole was imaged by the Event Horizon Telescope. One of the big problems is that how do you have this supermassive black holes formed at the centers of these galaxies? In fact, there are galaxies which were formed when the universe was only about 500 million years, and these galaxies have supermassive black holes. So this is one of the mysteries, that how do you form supermassive black holes when the universe was uh, as young as only 500 million years. But let me tell you that today's age of the universe is estimated to be about 14 billion years. Here is another spiral galaxy. You can see several spiral arms of these galaxies. Uh, Here is an elliptical galaxy with a dust lane, and this elliptical galaxy, for obvious reasons, is called sombrero galaxy because it resembles a Mexican hat. Here is a deep sky view uh, of the universe, and you can see elliptical galaxies, spiral galaxies. So just like for a biologist, it is the cells that are the basic unit of life. To understand the large scale structure of the universe, large scale distribution of matter of the universe, the typical unit cells are the galaxies. Each galaxy houses more than 10 to the power 11 stars, and of course, dark matter, halo. And the formation of galaxies, although there are a lot of theoretical models, but it's not clear what is the exact role of the uh, the the dissipation of the baryonic matter that is falling into the gravitational well created by the dark matter. And galaxy formation is one of the outstanding problems in cosmology. So here is a galaxy cluster. Uh, Many of the galaxies, they are bound to each other and they form a cluster. So rich Abel clusters contain 1,000 or more galaxies bound to each other. Of course, there is also dark matter. If the dark matter was not there, then all these galaxies will fly apart because the dark matter provides the gravitational binding to these galaxies. So this is one of the galaxy cluster named SMACS 0723, which was recently observed by the James Webb Space Telescope. So this is an image collected by the James Webb Space Telescope. You can see some of the arcs. These arcs are nothing but gravitational lensing image of a background object. The lensing is due to the cluster as a whole. Yeah, here is the central region of the M87 elliptical galaxy, and you can see the jet coming out. And as I said, the M87 elliptical galaxy at the center, it has a supermassive black hole which weighs 6.5 billion solar mass. That means it is 6.5 billion times heavier than our sun. You might ask that how is it that when you have a black hole, there are these emission taking place? So this is a artist's conception of what is happening. If you have a black hole at the center, then matter that is falling in towards the black hole, most of the matter would have angular momentum, so they can't radially fall in. They will form a disk because of their angular momentum, and the disk the inner disk will be moving faster than the outer disk. Simple Kepler's law, right? And because there's a differential motion, therefore there is viscous rubbing, and the disk therefore becomes hot because of viscous rubbing. Just like when we rub our hands with each other, it becomes hot. So the inner disk will be moving faster than immediately the disk, which is the ring next to it, and the differential motion causes a lot of viscous heating, and the disk becomes very hot. The magnetic field lines that get warped about, and therefore it is these that gives rise to some kind of a central engine that drives the jets out of the accretion disk. So this is an elliptical galaxy. You can see the fuzzy white thing, that's an elliptical galaxy. From the central region, you have two powerful radio lobe. Although these are radio emission, but radio emission has been given false orangish yellow color. And at the center, the Hubble telescope has seen resolve, not quite, but resolve that. You can see the dot inside that dot is the accretion disk. Of course, you can't see the black hole because that cannot be resolved. So there are many such radio galaxies, and it is today the consensus to explain the radio galaxies and the quasar. The consensus is that there is a black hole and there is a accreting matter, and because of the differential motion and the magnetic field, the matter gets heated up. And let me see whether I have a better picture. Yeah, unfortunately, I don't have a slide that tells you how the jets are collimated because of the helical magnetic field. So the jets are collimated because the magnetic field gets warped about, and the magnetic field form a helical structure, so that the charged particles, because of the Lorentz force, they cannot cross the helical magnetic field. They're collimated because of the helical magnetic field. And that's how you have collimated jets, radio jets, coming out of the accretion disk. All right. And now that I am in short of time, I'll quickly go to cosmology itself, about the universe itself. And since we were talking about radio galaxies, uh, India has two major sites where you have radio telescopes. One is the older radio telescope, the Uti radio telescope, and then we have the giant meter radio telescopes near the Kodad village in Maharashtra. And all these were indigenously built by the guidance of the father of radio astronomy in India, late Professor Govind Swarup. And radio astronomy has been very fruitful in telling us about active galactic nuclei like quasars, blazars, and supermassive black holes. And this is a uh, long view of the large scale matter distribution. You can see the bright regions are where galaxies are there. You can see the uh, filaments where the galaxies are present. Okay, so let me skip all this. Let me go to the universe as it is. And because I talked about James Webb Space Telescope, this is a picture of the James Webb Space Telescope. As you can see, this collects infrared radiation, and focuses into this point. And the mirror has a diameter of about 6.5 meters. Yeah. So, how do we know that the universe is expanding? It so happened that Hubble, Edwin Hubble, when he was taking the spectra of stars and gaseous objects in other galaxies, he found that the spectra were shifted to the red end, and uh, from the shift, he interpreted the shift as the Doppler shift, and uh, he fitted the Doppler velocities. Today we know, of course, it is not Doppler shift, but something else. And when he uh, found the estimated Doppler velocity and plotted them against the distance of the galaxy, he found a fantastic linear correlation. And he essentially interpreted it as the velocity of recession equal to some constant into distance. This constant today we call it as Hubble parameter. And the Hubble parameter's value, again, there is a great deal of mystery as to whether the value is about 68 kilometers per second per megaparsec, or is it 73 kilometers per second per megaparsec. There are these two different values we get if you study them using microwave background radiation, or if you estimate using galaxies. And this is called the Hubble tension, and it is another mystery. And everyone is looking towards resolving this Hubble tension. But coming back to the discovery of expansion of the universe, Hubble's result told us that further away a galaxy is, bigger is the estimated recession velocity. But today we know that this red shift, the shifting of light wavelength to the red end, was not due to a Doppler shift. Rather, it is because the distance between galaxy itself is expanding. It is a general relativistic effect. And because the space itself is expanding, therefore the wavelength of light gets stretched. And it is the Hubble law which tells us that the universe is expanding. All right. And uh, today we know that universe is not only expanding, but the rate at which expansion is taking place today is increasing with time. That means uh, there seems to be some exotic matter which causes repulsive gravity, because only if you have repulsion, the uh, expansion will have an increasing rate. If there was only attractive gravity, even if it is expanding, the expansion will slow down. But here, the expansion seems to be increasing, expansion rate seems to be increasing with time. And that's the reason, and this is allowed in general theory of relativity, provided you have some exotic matter for which 3 times the pressure plus energy density is negative. And such an exotic matter has been termed as dark energy. So, dark energy is that exotic matter for which 3 times pressure plus energy density is negative, so that it causes repulsive gravity. So, in other words, that apart from dark matter, which causes, of course, only attractive gravity, there's something else also which is dark. It's called dark energy, that causes repulsive gravity, because 3 times pressure plus energy density is negative. And again, it's a mysterious substance, because we don't know what this dark energy is, just like we don't know what the dark matter is constituted of. We only know that the dominant matter, the dominant energy density is that of dark energy. About 75% of the entire density of mass density of the universe is constituted of dark energy. That means 75% of energy density is dark energy. About 24.5% is dark matter. Only about 0.05 fraction, that means only about 5%, is matter that we are familiar with, namely matter made out of electrons, protons, and neutrons. So, as you can see, that we don't understand about 99% of the matter that constitutes our universe, we have no idea what is their real nature. And that's the reason why uh, the cosmic world presents us with a great deal of mysteries. And the only way to uh, get to the bottom of these mysteries is have more powerful telescopes, whether it's standard telescopes like radio telescopes, optical telescopes, infrared telescopes, or neutrino telescopes that detect neutrinos, or gravitational wave telescopes like the LIGO detectors. As you know, India itself has a LIGO India project, and soon it'll be operational. So the only way to learn about the mystery, to understand or resolve the mysteries of the universe, is to get acquainted with laws of physics and develop skills in mathematics and computation, and do a lot of observation, lot of experimentation. And that's the only way to resolve the various mysteries of the universe. I think I will stop. What is more important is that you should ask questions, because remember, I always take the attitude, don't believe in whatever I have said, you must challenge me. And skepticism, that means not believing, is the only way to discover new and new things in science. So thank you for your attention.
Thank you, sir. It was really enlightening, and I'm sure all the participants at the planetarium right now and on YouTube channel have learned so much. I think we should open the stage for question answers now. So I request everyone who's on YouTube channel can write their questions in the comment section, and Rishabh, who's present at the Planetarium Theatre right now, can direct the questions to us.
Don't hesitate to ask even trivial questions. All questions in science are important.
Hello, sir. Thank you for the
Yeah,
amazing session. I'm Dhanan.
thank
I
you.
am
Thank
having
you.
a small. Uh, we have spiral galaxies, which are like very famous. Thank you for the
Yeah.
amazing session. So we have
Thank you. Thank you. There are double voice appearing.
spiral
I don't
galaxies, which are
know.
like very famous. Thank you for the amazing session. So we have.
There are double voice appearing. Suddenly everything has got become quiet.
Yeah, it's just a technical glitch they are working on. I
Yeah.
think the speaker is
So
on.
spiral
Yeah.
galaxies are like
Go ahead, ask your question.
yeah. So spiral galaxies, the spiral shape is very common as we see in the universe. Now, why is it that those galaxies are not just disk and those spiral arms are there instead of just
Yeah, that's
it
a very
being a
good
very
question.
plain
That's a
disk?
very good question. There is a theory that was developed by Lin and Shu. Uh, it's called the density wave theory. And so let me go to a spiral galaxy, and I'll, in words, I'll try to explain uh, what exactly is their theory. Yeah. Uh, So Lin and Shu, their theory of spiral structure formation in a galaxy is the most popular theory of spiral galaxy formation. So it is like this: if you have a disk of matter going around the common center, obviously the disk matter will have differential velocities. And the differential velocities, because of the gravity and acoustic modes, there'll be a compression of gaseous wave that goes out in a spiral structure in the density. It propagates like a spiral structure. It's like a wave, actually. And this density wave uh, goes out in a spiral pattern. And wherever the density is higher, the gaseous density is higher, there the star formation becomes larger because the Jeans instability. If the density is larger, then Jeans instability tells us that stars will be formed. So this spiral pattern is where you see young stars are where the gaseous density is higher compared to the gaseous density between the spiral arms. And it is the Jeans instability that causes the higher gas density region to collapse to form stars. So this is called the Lin and Shu model of um, uh, the spiral arm formation in disk galaxies that has rotation, sufficient rotation. You can have a very simplified uh, description of Lin and Shu model of spiral structure formation if you read Frank Shu's book, The Physical Universe. I advise all the participants to read Frank Shu's uh, book, which is a very elementary way of presenting the entire field of astronomy and cosmology to students who are from 11th standard onwards. And in this book, the Lin and Shu theory has also been described in a very simplified form. So, in other words, it is the interplay of gravity and the uh, acoustic modes of waves propagating. All right. It is these two and the rotation, differential rotation, that gives rise to a density wave that propagates in the spiral form.
Thank you, sir. We have a few questions on YouTube comment sections.
All
So
right.
let us take a few questions
So
from
back to
there.
the fifth slide of your presentation. There are some black boxes like
Sorry.
so back to the fifth slide of your presentation. There are some black boxes like on the top left corner. Is it just because of the insufficient data? Or what's the
No,
reason
no,
for
no.
that?
This 62 slide, for example, because this laptop is not able to process that image. That's the reason why this remains blank. Is that the question as to why this slide there is nothing visible?
No, sir. Back to the fifth slide.
Is that the question as to why? Which slide?
Fifth, fifth one.
There are one or two slides. The display is not there because this this laptop is not able to handle the image. More questions?
Yeah, Rishabh, can we take some questions from YouTube now?
Due to some reason, I'm not able to access those questions. So you have to,
I'll put it online now, sir.
yeah, yeah.
So the first question is from Sayan. He says, "Hello, sir. I'm Sayan. My question is: does changes in dark matter and dark energy affect the nature of galaxies that are formed?"
Uh, by changes, do you mean the distribution of the dark matter and the dark energy changing with time? If that is what the question is, yes. In fact, uh, the dark matter, it is believed that the galaxies were formed because when the universe was very hot, the standard matter could not come together because standard matter are made out of protons and electrons, which interact with photons because photons interact with charged particles. So whenever proton and electrons will try to come together, the photons, where the matter was very hot, the photons will again make them push them away. But the dark matter, by definition, dark matter is something that doesn't interact with light. So dark matter, the density, they kept on, once they come together, density keeps on increasing because it's purely attractive. So the density increasing caused the potential, gravitational potential well became deeper and deeper because the dark matter density kept on increasing. In this deep potential well, the standard matter like electrons, protons, neutrons started flowing in. And that's how the galaxies were formed. So indeed, it is the change in the distribution of the dark matter that caused the formation of galaxy. Similarly, uh, of course, we don't know whether there is something called dark energy or whether it's purely cosmological constant. But if there is a dark energy that whose distribution is inhomogeneous, then the inhomogeneity of the dark energy would cause different kind of expansion rate at different region. So that would be essentially causing some kind of a anisotropic expansion locally if the dark energy is clumpy in nature. So indeed, the uh, the exact nature of the distribution of both dark matter and dark energy will affect the standard matter and galaxy formation.
Right, sir. Okay, I'm moving on to. I have a bunch of questions here. So the next question is: black hole absorbs all the radiations and radiates out some also. So which type of radiation they are they emitting? Um, and there is a follow-up question to this question from the same person asking: is there any limit to absorption in black body?
Yeah, so let me go step by step.
Yeah.
The black hole, as we know from general relativity, once matter crosses the event horizon, it just cannot come out. So, in other words, black holes by themselves, from general relativity point of view, can only absorb, it can't emit. Okay, so the quasars and radio galaxies that we see, it is not directly due to the black hole, it is due to the hot matter that is going around the black hole that is causing the emission. All right, it is not the black hole that is emitting. Black hole is only providing the deep gravitational potential. Well, yeah. So imagine that there is a central black hole, and it is the matter which is spiraling into the black hole. Because the black hole is very compact, you can go very close to the event horizon where the gravitational potential is very high, and therefore you can the matter will be going very fast and become heated up. It is that matter which emits, not the black hole. But there is something else which Hawking had mathematically shown, that if you take quantum effects around black hole, okay, not pure general relativity and black hole, but you take do quantum theory around black holes, then Hawking had showed that the event horizon, when you take quantum effects into account, the event horizon acts like a black body, and uh, it emits particles. Okay, once you take quantum effects, but remember that the Hawking temperature of the event horizon, when you take quantum effects into account, Hawking temperature is inversely proportional to the mass of the black hole. In fact, the Hawking temperature is 10 to the power 26 degree Kelvin divided by the mass of the black hole in grams. What does it mean? It means that if you take a black hole whose mass is as heavy as sun's mass, sun, as I had told you, has a mass 2 into 10 to the power 33 gram. So 10 to the power 26 divided by 2 into 10 to the power 33 gram is half times 10 to the power minus 7 degree Kelvin. That is ultra cold. You can't even detect such black holes. So solar mass black holes cannot be detected using the Hawking uh, particles that are being emitted. They are too cold. Only way to see Hawking radiation is if you have black holes whose mass is lower than about 10 to the power 16 grams. Okay, such black holes have not been detected as yet. They are called primordial black holes, or black holes that were formed when the universe was very young. So Hawking radiation is due to quantum effects. Classical black holes can only absorb, they can't emit. But once you take quantum effects into account, then there is the event horizon also has a temperature. Of course, the temperature is inversely proportional to the mass of the black hole. The last question was whether what is the limit of the absorbing power of a black body. If you take a thermodynamic black body, then as it is absorbing anything, any radiation, it is becoming hotter and hotter, right? So if it is absorbing more, then it is becoming hotter. But if it is becoming hotter, it is emitting also more. So the net effect is it can absorb anything, but it will also emit. And what you see is the net effect, that it is absorbing, becoming hotter, and emitting. So you have to figure out which is more. Is it the rate of emission is more or rate of absorption is more? When the black body is in equilibrium, then of course the rate of emission and rate of absorption is exactly equal. I hope I have answered all the three questions.
Yeah, sir, we have a lot of questions, but since we are running out of time, I think we can take last two more questions if that's okay with you.
Oh, yeah, yeah. Any number of questions is okay with
I
me.
know.
Yeah,
I can see.
yeah,
I mean, unfortunately, I cannot take all the questions, so I'm just like randomly
right.
picking
No, no,
it.
absolutely, absolutely. Yeah.
And that's just yeah. So this is from Ayush Gupta. He says, "Can you explain how jet streams are produced by the black holes, and if it can only absorb, not emit?"
Yeah. So are you able to see the slide?
Yes.
So the model is that there is a black hole at the center, which you can't even see in this picture, because the event horizon size, as you know, for a sun-like black hole, the event horizon radius will be only 3 kilometers. So here the black hole itself is not shown. And here is matter going around the black hole. And as I said, the matter as it grows around, because of the differential motion, it becomes uh, hot. And if it carries a magnetic field, because of differential motion, the magnetic field gets wrapped around the black hole, and it forms a helical structure. So particles, because the matter is so hot, they get ionized. So there'll be electrons, protons, and the helical magnetic field, they will help in collimating electrons to flow in jets. Why? Because you have a helical magnetic field. A charged particle cannot move across the magnetic field because there's a Lorentz force, which is V cross B. V is the velocity of the particle, cross magnetic field times the charge of the particle. So therefore, charge times V cross B is the Lorentz force, and therefore charged particles can only move along the magnetic field without force but can't cross the magnetic field. So therefore you have a helical magnetic field. It helps in collimating the charged particles, and that's how the theoretical modeling tells us how collimated radio jets are seen, because the charged particles which are gyrating and moving collimated, the gyrating electrons produce synchrotron radiation that uh, appears as radio emission, and that's how we see this radio jets. Radio jets are essentially charged particles gyrating and moving along this direction in a collimated manner. Remember, when you see the radio jet, what you see are the radio emission. You don't see the charged particle. But how do you get the radio emission? Radio emissions happen because the charged particles are gyrating around the magnetic field, again because of that Lorentz force. And gyration means the charged particle is accelerating, and accelerating charged particles always radiate electromagnetic radiation. That's how gyrating charged particle around magnetic field produces the synchrotron radio emission. I hope I have answered your question.
Yeah. Sir, we'll take one last question for today's session. And I'm hoping that all the participants who are asking questions here, sir may not be able to answer now, but during the course of this boot camp, a lot of things will get answered automatically in the coming session with the rest of the experts who will be here. So this is from Harshita Gupta. She's asking that you said that supermassive black holes were there when universe aged 500 million years. So does that mean that these black holes already existed before the universe? So it's a good
Yeah,
question.
so good question.
Yeah.
So, James Webb Space Telescope recently detected a galaxy uh, whose light was emitted to reach the telescope when the universe was only about 450 or 460 million years of age. And this galaxy has a million solar mass supermassive black hole. The question is, how do these large black holes form? It's still a big mystery. And there are many models, including some of the work my student and I have done, where we invoke the Bose-Einstein condensation of ultralight dark matter to give rise to these supermassive black holes. But more popular models of black hole formation is due to celebrated astrophysicists like Martin Rees and Begelman. Their model is of direct collapse, where they say that when a galaxy is forming, if you have a spherical distribution of matter, they can just directly collapse to give rise to supermassive black holes. Most astronomers believe in the direct collapse model to explain such supermassive black hole being detected at a young, but direct collapse models have their own problem. The problem is that uh, how do you ensure that there is no little angular momentum? Because if you have a little angular momentum, then you can't have direct spherical collapse. Similarly, the cooling, you have to have fast cooling to prohibit when this matter is collapsing, then uh, it should not, because of its own turbulence, it should not get heated up. It should sufficiently cool so that it doesn't get heated up and yet it collapses to form a supermassive black hole. So there are some problems associated with direct collapse models too, and that's the reason why my students and I, we have given alternate model where if the dark matter is made out of very ultralight particles like axions, then we can invoke Bose-Einstein condensation of these ultralight particles to give rise to supermassive black holes when the universe was very young.
Thank you, sir. Again, I cannot take all the questions today, but I'm sure, sir, if possible, we'll send them over. And
Sure,
if you can
definitely.
please answer these
Sure,
questions, that'd be great.
sure.
All right. Thank you, sir. Thank you for
Most welcome.
giving your most valuable time for this session.
It was my pleasure. It was my pleasure.
Most welcome.
So, thanks to all three of you, Prerna, Rishabh, and you, Megha. Take care. And take care, all the students and audience members.
Sure, sir. Thank you.